Dear students, today we discuss an advanced topic on friction stir processing for fabricating surface composites. Composites are a very important class of materials used in versatile engineering applications. So, I am going to discuss one of the important technique for fabricating the composites. So, the outline of my presentations covers introduction, friction stir processing, processing strategies, metallic reinforcement, and at last conclusion. So, the basic of composite, or what is the composite, is simply it is a mixture of two or more material. This is a very simpler definition of the metal matrix composites. See, in this figure you can see that there are reinforcement may be of ceramic particles or metallic whatsoever be. It is different from the matrix material. Suppose for example we can take that this the matrix is of aluminum alloy, any alloy you can take it. This is of aluminum alloy, and the reinforcement is of silicon carbide. So silicon carbide ceramic particles are mixed in this aluminum alloy to make a metal matrix composite. So these are the primary composites which are used in many applications, just like piston in internal combustion engines. And now the second category of composite is the functionally graded composites. So in which there is a gradient of composition ranging from upwards to topwards, or from bottom to top. So these composites having a variety or the reinforcement in different volume at different places. Suppose as you see in the figure, at the lower part the quantity of reinforcement is limited or less. As we go on increasing to the top, the volume of reinforcement increases as we go on the top. So suppose in an application where we need the higher reinforcement or higher amount of reinforcement at the top, then this functionally graded composite will serve the purpose very well, because at the top surface or at the surface we need the highest amount of the reinforcement, but at the lower part we does not need such a great amount of reinforcement. So there is a variance in the volume of the reinforcement. So these are known as the functionally graded composites. Now again there is a category of the composites which is known as surface composite, in which only surface is reinforced with reinforcement. So as we see in figure, the reinforcement are limited to the top layer or the surface layer. So these are having application where the surface interaction is involved, in engineering application where surface interaction is involved and nothing to do with the rest of the matrix. So these are the very suitable class of material, and they are targeting a very good research potential because of the surface layer. Now we have to talk about the technique which makes these composites, and one of the most important technique is friction stir processing. In friction stir processing, as the name suggests, friction, stir, and processing. It combines three words. So there is friction involved, and stirring involved, and last processing. So by combining the friction and stirring process, this processing is completed. And how this can be accomplished or achieved, we have to see the figure. In this figure you can see that there is a tool which rotates at a high speed RPM, and due to rotation, when it contacts with the surface, it will generate friction due to movement, and because of this friction, low melting alloys such as aluminum will soften, because of the heat generated is so much high, or so enormous amount of heat is generated that it will be softened, but it cannot be melt, because the heat is not so much high that it can melt out. So that's why it's also termed as a solid state processing, because the material will remain in a solid state. It will soften, although it will soften, but it will not going to melt. So uh, it is a type of a solid state processing, in which in the schematic diagram you can see that there is a tool which rotates, and we are making a surface composite. So we uh, drill holes in the surface and we place some reinforcement particle in that holes, and when this tool starts from here and it goes at last, a composite layer, a surface composite layer will form on the surface. So this is the basic process of for making a surface composite by the help of by using the fixed resistor processing. And now a second method is also there, that is groove method, in which we make a groove. As you see in the figure, we make a groove and place a reinforcement particle. It is a continuous groove, and we have to pack this groove by a pinless tool. You see, this is the pin or probe. So when we use a tool without probe, it will close this groove, and finally we use the tool with a pin or probe when we process it. So these are the two basic methods for making mostly used method for making surface composites by fixed resistor processing. Here the heat is generated by the rotating and movement action of the tool. Here heat is generated, it is where it makes the contact with the matrix material, and so due to the movement of the tool, heat is generated due to the friction. And this probe, as you see in the figure, this probe will stir the material, because it is also rotating with the tool, and it will stir the softened matrix and also the reinforcement particle. So there is a sort of stirring and high RPM stirring, which uniformly mix the reinforcement with the matrix material. Here we have to note that one thing, that the bettability issues of ceramic particles with the matrix in the liquid state processing, this will not this problem will not encounter here, because the matrix material is in solid state, so there is no wettability issues. And these are the process parameters which can be considered for making surface composites or FSP, and these are some variables: and tool rotational speed, at which RPM it is rotating. If it rotates at high speed, then high amount of heat will be generated. Tool traverse speed, if the tool traverse speed is low, then a high amount of heat will be accumulated, and if its tool traverse speed is fast, then it means that the tool is moving fast, and the heat generated amount of heat will be very less accumulated there, so the low heat region will be there. Tool tilt angle, generally a tool is tilted through a central axis by 2 to 3 degree, and it is necessary to accommodate the material. Tool plunge depth, how much the tool is inserted in the material, that is a very important parameter, because if we not sufficiently plunge the tool in the material, it will not form a sound processing part. So other parameters related to the tool design, and the number one is shoulder. So then shoulder diameter and profile. So profile plays a very important role. We will discuss it later on in the tool geometry section. In the diameter, more the diameter, more the contact, and the more the heat will be generated. But we have to spend some more power on it. And the probe diameter, probe profile, and probe height. So when probe diameter increases, it will consume more power. When the profile, so we have to select wisely what profile can be used, that the ceramic particle can be uniformly mixed, and the height means the geometry, which height 3 mm or 4 mm or 5 mm, because if more is the height, and there will be more chances to be that this probe will be broken out. And the material properties, what is the material we are processing, it also depend on that. These are some important variables. These are the tool geometry. So you can see threaded one, you can see triangular one, you can see square one, you can see plain cylindrical one, and conical one. So there are a lot of tool geometries are there, and there are many more geometries are there. We are discussing some few which are mostly used. Square one, triangular one are mostly used. Threaded one, this is fluted one, which is also used. So this is the simple tool which you can see that this is the shoulder and this is the probe or pin, and there is a concave type profile. This is necessary to accommodate the softened material. So this is the basic tool geometry of the friction stir processing tool. These are the micrographs of aluminum alloy, which after processing without making composite, we generally process without using reinforcement to see the effect of the grain refinement. See, this is the base alloy which is having a large grains, but when we only single pass of FSP is applied, see, you can see that the grain size is reduced significantly. So this is the effect of friction stir processing. The friction stir processing refine grains to a greater extent. This is because of the dynamic recrystallization process occurring. So the recrystallization process occurs during the process. That's why it's called the dynamic recrystallization. And due to dynamic recrystallization, the grain size of the aluminum alloy is refined to a greater extent. And we apply multiple passes. Suppose we apply 4 passes, and after 4 passes you can see that continuous dynamic recrystallization occur in this processing zone, and it will finally make the grain size so much equaxed and so much refined. So you can see that there is about 10 to 20 times of refinement in the grain size. And these are the micrographs of some surface composites which we manufacture. This is the process zone, and in this zone we have captured some images of the areas which are not well processed, so to see the defects and what are the causes of the defects. So we have to see that there is a deformation, there is some cluster formation of silicon carbide, and this clustering is due to the or clustering or some reinforcement agglomeration is due to the improper selection of the process parameter, as we discussed earlier. This is similar the case in the TIC reinforcement is there is some agglomeration or the clustering of particle, whereas in this there is some uniform distribution. You can see there is uniform distribution of the reinforcement particle. This is the schematically when we put some particles in a hole and when it rotates the axle of the tool, they moves like that in that fashion, and they moves like that. So this is the schematic presentation of the ceramic reinforced particle moves in the during processing. These are the micrographs which are formed due to by using the friction stir processing. And this is the EDS map. This shows the uniform distribution, a very high magnification EDS map. And this shows the schematic how the high rotational speed can helpful in making a surface composites with uniform distribution, because of high strain action the particle will move upward and they will be distributed uniformly. And this is the friction stir processed material of aluminum silicon alloy. You can see here acicular silicon is there, but after friction stir processing these acicular silicon is break up into small fragments. So these are some micrographs and the bond surfaces and the wear mechanism. These are some micrographs. So finally we can conclude that the friction stir processing is very important technique for fabricating surface composites, and it is very for having a sound processing. The process parameters must be selected very carefully. So thank you very much for kind attention, and